Welcome to part 2. So in this video we're going to go over what this project is. So what are we building? We're building a 3D printer with roughly a working area of 3 foot in Y, 6 foot in X, and over 2 feet in Z. So the whole design goal of this printer is to put down a lot of material really fast. So this isn't going to be a super high resolution fast printer. It's going to be a decent resolution high volume printer. So I have some projects coming up that I want to print roughly 2 foot in Y and 5 foot in X. And I want to do it without it taking over a week per piece. So my first thought was big nozzle, a lot of heat, push as much filament as possible. And that is the route that I've taken. So the whole project started with research. I researched this for weeks. I looked at printers such as the Havort, which is a phenomenal fast printer. It is high resolution and moves lightning quick. It's a very flexible printer. The designer has created the bed on a 3-point system with a lot of articulation, I believe with the goal in mind of eventually for non-planar printing, which would be really cool, but not great for my application on such a large frame. So I took inspiration from this printer. This is a Core XY style printer, and from the beginning I was pretty sure that this is the kind of printer I wanted to build, a Core XY. So I also saw this printer, Dash X. I'll include a link to his video in the description. So this printer uses a dual belt system, one for X, one for Y, and then almost in a binding motion causes the carriage to move back and forth. And I was set on this design for the longest time, except for one key detail that I wanted, which was I wanted to be able to reach into the printer without the gantry getting in the way. So this makes things tough without having a front cross rail. So back and forth, playing with a lot of little designs. I finally settled on something, and that was based on the Boron. So the Boron 2.4, except for its size, the structure of it did everything I wanted. So it has an open frame in the front. It's a Core XY, so it's fast. I didn't want these travel speeds from one end to the other to take forever. It has to be fast. So in my other background of machining, you waste a lot of time in rapid motion of the machine. So if you can't move from one side of the printer to the other side of the printer quickly and efficiently, you're going to waste a lot of time on these giant prints. So Core XY seems to make the most sense. A lot of people are very leery or advise against the longer belts of a design like this. My thought is this is amazingly inexpensive to build a gantry like this. The machine itself, in total, very expensive. The gantry part, I don't think I have more than $200 into the entire gantry structure. This be here, the XY platform. So if it doesn't work, I'll revise it and go to something different. So I'll break it down a little bit. I'm going to jump back and forth here. So this machine wasn't designed to be a toy. This was designed to be a workhorse. So in my opinion, I bought the best equipment that I could get. So to start, we have a Duet 36HC mainboard as the main controller of it, and this will have a Raspberry Pi 4 SBC hosting the web interface and feeding the code to the 6HC board. On the toolhead, we're going to use the Duet toolhead board. So this allows me to run power and CAN up to the extruder, and also take a touch probe, which I will be using a BL Touch. So all that right on the tool head. And then later on, if I do want to do some kind of tool changer setup, I'm already built for it. But this means I don't have to run super long stepper cables, heater cables, and all that. If you look at the design, this is 72 inches wide. By the time cable management is in play, you're talking about cable runs that are 2.5, 3 meters long easily, if not closer to 5. So it made the most sense to run as few signals as possible, as few wires as possible, up to the gantry and to the tool head. So that's why we went with the tool board. So now we have to push material as fast as possible in a printer that has over 4,000 watts of bed heat with a chamber heater. This meant one thing in my mind: water cooling. So Titan Aqua extruder, this is what I went with, and this will be my primarily extruder for now. I wish I could get a water-cooled dual drive, because I think the single drive is going to be my downfall right now. But for now, we're going to start with this, and we'll go from there. So we went with the 1.75 millimeter, 24 volt, standard orientation, obviously, because we're doing direct drive extruder. But this only has a V6 nozzle on it, factory. Not going to have enough volumetric flow for my application. So we went with the E3D Super Volcano. So I got the Super Volcano eruption kit, which comes with 5 nozzles, I believe. 0.8, 1, 1.2, 1.4, 80 watt heater, and we did everything on the printer for controls in 24 volts. It's the only way to efficiently get this kind of power out of the system. So Super Volcano with the Titan Aqua extruder. In my testing, I'm able to get 55 to 60 cubic centimeters per second squared volumetric flow, which is mind-bogglingly fast extrusion. So that pretty much goes over the hardware. I mentioned we got a BL Touch. We will be doing mesh bed leveling on this system. But like I said before, this medium resolution, medium quality, a lot of material. So I want to be able to extrude between 0.2 and 0.8 millimeter layer heights, and I want to be able to extrude it at 1.6 to 2 millimeter layer widths. So if the bed's not perfect with the gantry sags, it shouldn't be a problem when I'm printing those larger layers. For the finer layers, the 0.2, those will probably need some compensation in there. We'll deal with that when the time comes. So that's my plan, and I'll get into design a little bit now. So